Good morning. I am in this video going to demonstrate the use of StatCrunch in order to compute a regression, as in chapter 4. And the problem will involve taking the data from the assignment, loading it to StatCrunch, and using simple linear regression procedure that is within the stat set of StatCrunch commands. So first, I'm going to head over to our shell and canvas and Pearson my lab. I'm opening my lab and mastering. I'm trying a reload because there is some error in the loading process that can commonly happen all the time, as you know. And I'm going to go to the assignment lab 4, where I'll be working 3 distinct kinds of questions. One sort of question that I'll be working with is a question that employs StatCrunch in order to calculate everything within StatCrunch. And another question, I will start with output, and from the output, I will then go through the regression output that is given and have StatCrunch do the arithmetic through the data command. Before I begin, I would like to review a little bit about the concept of correlation by using question 5 in the lab. In this question, you see 4 different scatter plots, A, B, C, D, and you see 4 different values of correlation, and your job is to match them. So the more linear the shape or form of the scatter plot, the closer to either +1 or -1 you should identify the correlation value. So for example, graph C corresponds to data which shows high linearity in form, a positive slope, i.e. a direct relationship between the variable on the x-axis and the y-axis. And so my best guess for part C would be the correlation labeled 0.951. And then the mirror image of that file is in graph D of part C is in part D, where you see high linearity and negative slope, and thus a very strong inverse relationship consistent with a negative 0.923. In addition to that, we now see graph A having a strong form, but it's not linear. It's a little curved and in a positive sloping way. So the correlation for part A, for the graph in scatter plot A, should be positive and not necessarily super strong like a 0.9, but relatively strong like a 0.736. And last but not least, the least linear of all the graphs in the scatter plot set is scatter plot B. And so that's going to be really close to 0. And that would be consistent with the minus 0.02 negative correlation. So this graph is very consistent with one of the set of notes where I match the shape of a scatter plot, the form, the direction, and the strength of a scatter plot with that of a correlation value. So I hope those notes are, upon your review, useful in that regard. So I'm going to move now back to a question where we estimate the different statistics in a correlation. You may recall that I mentioned that in a regression analysis, there are 7 statistics. So the first one that we usually estimate is the slope of a regression line. And so to do that, to calculate the slope, I'm going to upload the data into StatCrunch. Then I check for any cautions that any risks, any problems that I might have. The problems might be such as linearity, because you notice how linearity creates lower correlation value. Another problem could be outliers. The presence of outliers can be problematic. Another problem could be unequal spread, where you see very thin linear form in some subset of the data, but then very bulky variation in other parts of the data. And so you see uneven spread throughout the linear form. That would be something that you're cautious of. Those are the three main precautions: outliers, nonlinearity in the pattern of the form, and unequal spread around the linear form of the data. So now that I've opened, that I've clicked here and been able to open in StatCrunch the data, let me go there. And at this point, I'm going to just assume that none of those three complications or cautions are present, and I'm going to go straight into running StatCrunch. So I go stat, regression, simple linear. I pick my variable X to be the hard drive capacity, and the predicted value, the predicted variable is price. I compute. And the 7 summary statistics are given to me in the highlighted region, including the slope. The slope here is 104.06. The slope is what connects the X factor to the Y factor, the rise over the run. What tells us how price changes with respect to capacity. So in this case, I go back to the homework problem, and I put in 104.06 to round to 2 decimal places as needed. And it asks me, what does the slope mean? It indicates the additional price for each terabyte additional of capacity. It's the rise in price due to a rise in capacity. In this case, rise to rise, because it's a positive slope. So there's a direct relationship between how big a hard drive is storage-wise and how expensive it is. Then it asks me for what the intercept is. So I do the same exact thing as I did for the slope, go locate it in the equation of the linear regression that predicts price from capacity. And that would be the price of components that are unrelated to the capacity of the hard drive. In other words, the price of a hard drive is a function of 2 things in this model. The capacity of storage is one, and everything else. So all other things combine to about $21.30 in the price of a hard drive. So it indicates the price for a hard drive where you're not taking into account anything about capacity, but all of the other parts that are common to drives independent of capacity. Now I'm going to put in the line. So it just asks me to essentially put in both the intercept and the slope into the equation of the line. And then it asks me for to predict the price of a hard drive that is 1 terabyte in capacity. So 1 terabyte would make this capacity variable here a value of 1. So I'm just going to add $21.30 to $104.06, get $125.36. And that is my estimated or predicted price for a 1 terabyte hard drive. If I wanted to do that in StatCrunch, and if, for example, my hard drive were not as easy to measure the predicted price for as a 1 terabyte hard drive, what I would do is, let me go back to StatCrunch. What I would do is in the options of regression, after I set capacity and price as my X and Y variables, if I scroll down the option sets, there's a way to make a prediction. So I could put several values here, 1, 2, 4.7, whatever I wanted. I could make a list of numbers separated by commas and compute. And what I would then need to do in order to observe my predictions is simply look at them under the predicted values. And specifically, here's the $125.36 prediction for our 1 terabyte hard drive. But you can put in any number under options, edit, and you can make any prediction you want for one number or for several values. So that's how you make predictions using StatCrunch in the original units of the data in the problem. The next question is, what if you paid $110 for a 1 terabyte hard drive? Is that a good buy? And the answer to that is yes, because you were predicting or expecting the price to be $125.36. So paying less than predicted is a good deal. It's kind of like a good surprise. The next computation is that of what we call in this chapter a residual. A residual is the difference between what you actually pay compared to what you were predicted to pay. And so you're paying $15.36 less than predicted. The residual in this case would be a negative value, 110 minus 125.36. And so the way you write that answer down is not as a negative 15.36, but as a 15.36 less than expected. And in this case, are you underestimating the price or are you overestimating the price? Well, the answer is you're overestimating the price. How do I know you're overestimating? You're overestimating because you are estimating more than what you actually paid. So you're overestimating. So when the residuals are negative, you are overestimating. When residuals are positive, you are underestimating. So as you can tell with these questions, when they are computational, the process is very simple. Load the data into StatCrunch, boom, switch over to the data and ensure that you see data that has no crazy outliers, that has no variational changes in spread, where the spread is big in some parts and small in others, and where the data points don't align in a curved or nonlinear fashion. So you want to check for nonlinearity, outliers, and unequal spread. If those three types of problems are not present, then your regression is going to show a very high correlation where you can explain price very well. 97.8% of price can be explained with capacity. That's the meaning of the R squared. Where your errors are small in amount. So in this case, the average error in predicting hard drive price is $27. And where the model will be such that it looks very similar to the scatter plot of the dots. So that's how you use StatCrunch to completely analyze the 7 statistics that are presented in a problem. Now moving on to another question. I believe it's question 8 or question 7. It's question 7. In question 7, when you click on the icon, you don't get the 2 columns of data for each individual variable. What you get is You get the R-square, you get the standard error of the model, you get the slope of the model, and the intercept of the model. So you get 4 of the building blocks that are connecting the y variable. The y variable is the one that depends on the other one, and that would be developing economy growth. And the independent variable would be the one associated with the slope. In this case, the developed economies, or let's call them rich countries. So what I'm going to do next is begin from a blank StatCrunch. And what I'm going to do is set up some ingredients here. So the first thing I'm going to do here is make a list of things. And I need X, I need Y, I need a slope, which is called B1 in our textbook. I need a y-intercept. That's called B0. So I need a line that's basically B0 plus B1 times X, so that I can make predictions. So I'll call predictions Y-pred. I then need residuals, which are called errors, or are usually labeled with the letter E for errors, because R is correlation. I need a coefficient of determination, also known as an R-square, which is a percentage. And this percentage measures the percentage of Y explainable by X. And I need a standard error for the regression model, and that's an amount of Y that we cannot predict, or that we cannot explain with our regression model. So that's my list of items that I need to have in order to fully analyze a regression. So in this case, X is going to be, I'm going to make a column of definitions. X is going to be rich country, growth, developing country growth, the slope is going to be the ratio of developing to rich country growth. So it's always the rise over the run. Y is the developing growth that is not related to rich country growth. So I'm going to call it independent developing economy growth. And Y predicted is B0 plus B1 times X. And the residuals are Y minus Y predicted. Correlation is, in this case, not precisely given, but it's actually related to this percentage, to this 20.51% called the R-squared. It's actually the square root of 0.2051 R-squared. And in this case, it's a positive correlation because there's a direct relationship between the two values. So the R-squared is the percentage of Y explained by X. And the standard error is the percentage of growth in the developing world that is unexplained by rich country growth. So here are the values. And the value of X varies, the value of Y varies. Those are, as we see, in this case, those are the variables. That's why they vary. The slope is 0.497. The intercept is 3.88. And when we make predictions, We combine those with the values of x. So the top 3 out of the top 4 lines give us predictions. Okay, and so on and so forth. So what I'm going to do now is I'm going to make the window a little bit larger here and utilize, well, I'll keep adding information. 0.2051 is the R square. 20% of developing economy growth can be explained by the growth in rich countries' economies. And the standard error is 1.247%. In other words, when we're trying to predict how Russia, China, Brazil, countries like that are growing, our average error in making that prediction is 1.247%, which is a fairly large error given that it's only explaining 20.5% of what happens in developing economies. And to get this, we take the square root of 0.2051. So how do we find the correlation coefficient? We can go data, compute, expression, data, compute, expression, and then we just type SQRT of 0.2051. That's how you tell the software to calculate the square root of a number, and we're going to call that R and compute. And notice how that is 0.4529. So 0.4529. It's our correlation. And then we need to have other calculations done. In the meantime, let's go back to our homework problem and try to answer some of the questions that don't require too much computational work. First, write the equation for the regression line. Well, that would be that y equals b0 plus b1 times x. So rich countries times 0.497 plus 3.88 equals the percentage growth in growing countries. What is the meaning of the intercept? The intercept is the growth in developing economies that is independent of growth in rich countries. Then it says, does the intercept make sense? And the answer is yes, because it's positive. If an economy is developing, it should be growing, independent of what's happening in economies that either are already fully developed or that are not even, that are highly impoverished. So a developing economy should be growing positively, and it is in this case, as you can see. So it does make sense to have a positive y-intercept in this model. The next question is interpret the meaning of the slope, which is that if rich countries' economies are growing, well, rich countries will obviously not only buy the stuff they produce themselves, they'll also buy stuff all over the world. That's the definition of a developed economy, one that can buy from any economy and even further than that, export. But definitely their economic growth benefits the economic growth of all other countries. And so in this case, for every 1% of rich country growth, developing economies grow an extra nearly 0.5%. So when the GDP in developing countries grow by 0.5% due to a 1% increase in a developed country, or not necessarily due as in a cause and effect growth. But here comes the first interesting problem. They want us to predict a value for y based on a growth of 4% in rich countries. So they basically want us to calculate 3.88, the intercept, b0, plus 0.497 times 4. So the 4% refers to the x value, and the predicted value would be taking this entire calculation. So what I'm going to do is I'm going to go back to StatCrunch and go to data, compute expression, and paste the expression, and that's going to be my predicted value for x being 4. So when X is 4, when developed economies grow at 4%, developing economies grow at 5.868%. So that takes me back to the homework, and I'm going to put there 5.868, just like my calculation told me to, and it's going to give me a nice work. Be careful with this part, with this next part. In part E, it says, in 2007, the developed countries experienced a growth rate of 265. So that is the X value that you have to use in part E. While developing economies grew at 6.91%. So is this 6.91% more than you would have predicted? Well, if you go back to part D, you notice that when X was 4, the prediction for Y was 5.8. Now, in this case, X is even smaller than 4, and Y is bigger than 5.8. So this is clearly way more than you would have predicted with rich countries growing at 2.65%. If you don't want to reason through with logic for this, you can always go back to StatCrunch and go Options, Edit, and instead of 4, put in 2.65. And for X being 2.65, you will see the predicted value is only 5.197, which is smaller than 6.9%. And therefore, the growth of developing nations that are listed in part E, in my part E, is going to be comparing 5.197 which is my predicted value, versus the actual value of 6.91%. Okay. So I'm going to round this to 2 decimal places. And I'm going to notice that the difference is 1.71%. So clearly the actual of 6.9 is bigger, is more than the predicted of 5.2. And the residual then should be a positive residual, an underestimation of value. Okay. So thank you for watching this video. To review it, we did 2 activities. One activity was we ran a regression in using problem 3 of the lab. And now we used the data compute expression command to help us organize the information within StatCrunch and to help us with data compute expression run arithmetic computations. And I'd like to thank you for taking advantage of and watching this video.